Let's do an example together. That is example 2.28 from your book. So I've got it posted here. There is a tower. It's subject to earthquake loads that could be of high intensity, H, or of long duration, L. So high intensity earthquakes or really long earthquakes. It is estimated that if the load has a long duration, the earthquake load, the probability that its intensity is high is 0.7. And let's just highlight that real quick here. So we've got, okay, so if the load has a long duration, and that refers to the earthquake, the probability that its intensity is high is 0.7. And if the load has a high intensity, there's a 20% probability that it will be of a short duration. Finally, the probability of having a long duration earthquake is 0.3. So these are all kind of important values that we'll be using in a little bit. Okay, so the designer estimates the probability of failure when a tower is subjected to a short duration, high intensity earthquake is 0.05, and then that's doubled if the earthquake is of long duration but low intensity. All right, so we're gonna have to remember all those things or write those down. Also, if they are certain that the tower will fail if subjected to an earthquake of both high intensity and long duration. So certain that the tower will fail and that it will not fail or survive with certainty if it's subjected to a low intensity and short duration. Okay, so a lot of values here, we'll write them all out. So the problems of interest are the events L and H mutually exclusive? So H and L mutually exclusive. Are they statistically independent, and are they collectively exhaustive? And then finally, we'll calculate the probability of failure if there's an earthquake, just any earthquake in general. So first things first, let's write out the probabilities of everything that we're given. Let's start from the top. If the earthquake or load has a long duration, the probability that its intensity is high is 0.7. So the probability that we have high intensity given long duration is equal to 0.7. And I've defined those terms here. So H is high, L is long, H complement is low intensity, and L complement is short duration. Okay, let's keep going. There's a 20% probability that if the load or earthquake has a high intensity, then it will be of short duration. So that's going to be the probability that we have a short duration. So that's going to be complement L given high intensity. And then the probability of a long duration earthquake is 0.3. So probability of L is 0.3. And then we've got some other stuff here. Okay, so let's keep going. The designer estimates the probability of failure when it's subjected to a short duration, high intensity earthquake is 0.5. So let's write that out. So probability of failure, so F equals fail. Probability of failure given short duration, high intensity. So short duration and high intensity. Just make sure we all know that's an L right there. So it's short duration and high intensity. That's the probability of failure given that. That's pretty low, 0.05. And let's keep going. The probability is doubled if we have a long duration and low intensity. So probability of failure given long duration, short intensity is equal to double that previous one, so 0.1. All right, now last two things here. We're certain that the tower will fail. So the probability of failure if it's subjected to both high intensity and long duration. So high intensity, long duration, and that's equal to 1. And then probability of failure given low intensity and short duration. So H naught L naught is equal to 0. All right, that was a lot. All that was embedded in those prompts. Now that we've written out the probabilities, let's take a look at answering some of these questions. So the first question we have is A, are the events mutually exclusive? Or ME as we abbreviate it. Well, let's think about that. So mutually exclusive means that the events don't intersect. In this case, we're looking at H and L, so H and L. Do they not intersect or do they intersect? Meaning, do they have some commonality to them? If L happens, can H also happen? We can think about that logically. If an earthquake of high intensity happens, can it be long or short duration? Well, yes, the answer is yes. So logically it makes sense, but then let's look at what we've been given. So the probability of H given L is equal to 0.7. That's a positive value, real value. Therefore, we know that it's not mutually exclusive. If L happens, H can also happen. There's an actual probability of that. If they're mutually exclusive and L happens, then the probability of H given L would be 0. All right, so not mutually exclusive. All right, next question is, are they statistically independent? Or SI? And let's think about that one. We need to understand that for something to be statistically significant, then we can use kind of some of these numbers. The probability of L given H should be equal to the probability of just L, right? It doesn't matter that H happens, L can occur. So let's see what information we have. The probability of L given H is equal to something we have up here. Let's take a look. It should be equal to 1 minus the probability of not L given H, right? Because if H happens, we're given the probability of not L happening. So H happens, we have a low duration or short earthquake, high intensity, short duration. This is the probability of it being a short duration given a high intensity. And then the opposite of that would be a long duration given a high intensity. Okay, so we can calculate that as just 1 minus 0.2 equal to 0.8. So that is the probability of long duration given high intensity. And then, so that's this value. And so does that equal the probability of L? So 0.8, the probability of L, and let's look, that was actually given to us, right? Yep, 0.3. So no, 0.8 does not equal 0.3, therefore we are not statistically independent, all right? Okay, and then the last question there, or the second to last question is C, are H and L collectively exhaustive? Or CE. What that means is if we were to have a sample space, do H and L comprise the entire sample space, right? So probability of H plus the probability of L should equal 1 if they're collectively exhaustive. We already know they're not mutually exclusive, so there's some overlap, but are they collectively exhaustive? So that is basically the probability. Another way to write this is probability of H or L equals 1, right? So the probability of H or L is equal to, again, this only holds if they're mutually exclusive, but we know that they're not, so we'll just ignore that one. So probability of H or L is equal to the probability of H plus the probability of L minus the probability of H and L. All right. And because we know that they're not independent, then this equals the probability of H plus the probability of L minus the probability of H given L using the conditional probability rule times the probability of L. Now let's see what we have. Can I go back up here? We have H given L, okay. And we also have probability of L, so that's good. We don't have the probability of H though, so we need to figure that one out. And so all of this should equal 1, right? So this is ultimately what we're trying to figure out. All right. So probability of H, let's figure this one out. Well, let's think about what pieces of information we have and go back up here. We've got H given L, and we've got the complement of L and H, and we have L. So maybe we can use some conditional probabilities to figure out the probability of H. All right, so probability of H using some conditional probabilities. We'll go back to the conditional probability rules. The probability of L given H, that's something we have, is equal to the probability of L and H all over the probability of H. And then we can solve for H, which is what we're trying to find. And that is equal to the probability of L and H all over the probability of L given H. Okay, now we don't have L and H, right? So that's a little bit tricky. We do have L given H. Oh, we have H given L. So we're gonna keep working on that one. All right. Now let's take this term right here, which we don't have, L and H. We'll use conditional probability to set that one up. So this is the probability of L given H times the probability of H. We could also flip it and say this is the probability of H and L. So that's equal to the probability of H given L times the probability of L. We do have L, so that's something that we have. And we do have H given L, so that's good. All right, we're getting close. So let's substitute this back in for that. Probability of H given L times the probability of L. And then we have probability of L given H. So that was not defined. But what we do have is the probability of not L given H. And that is equal to 1 minus the probability of L given H. So now we can have got values that we can plug in here. So we'll just go back up. We have H given L is 0.7, not L given H is 0.2, and then L is 0.3. And again, we're going to plug this in. Up here, where we'll just do that final solving. So that's the probability of L given H is equal to 1 minus the probability of L not given H, which is just 1 minus 0.2. All right, plug in the other values. We have this one is 0.7 times 0.3 all over 0.8. And that gives us 0.26. So that is our probability of H. That was a bit of a journey, but we made it. Okay, now we'll just kind of box this out. That was a little side trip we took. Now we can go back here and calculate this stuff. Okay, so the probability of H or L is equal to the probability of H plus the probability of L minus the probability of H given L times probability of L. And we'll note that we've got all these values, so we can just go ahead and plug those in. So this is 0.26 plus 0.3 minus 0.7 times 0.3. And so all of that equals 0.35. Therefore, we are not collectively exhaustive, which is the original question, meaning all of this would have to equal 1 if it was collectively exhaustive, right? So we're not collectively exhaustive. Great. Last question, if we come back up here, is finally calculate the probability of failure if an earthquake happens. All right, so we've got a lot of ammunition to answer this question at this point. So we're going to calculate the probability of failure. And to do that, we need to basically say, what are the collectively exhaustive events that could happen? So if we take all the events that could happen, that could lead to failure. Or basically that, you know, if an earthquake happens, what are all the potential outcomes, right? So to calculate this. So first we're going to find, we want to find this probability. So probability of failure if an earthquake occurs. And the first step that we'll do is identify all collectively exhaustive events for this particular outcome for F. We just proved that H and L are not collectively exhaustive, but we're going to bring all the events together that would be collectively exhaustive. So we can have high magnitude, long duration. We can have high magnitude, short duration. Sorry, it's not a comma. And then we can have low magnitude or low intensity, long duration, and then low intensity, short duration. And then once we've identified all those events, these are all the possible outcomes, you know, given how we've defined this problem, now we can apply the theorem of total probability. Which says that the probability of, in this case, we'll just say F is equal to the sum of probability of F given some event times the probability of all those events adding up. In this case, these are our events, right? So E is a set of all of these things. These are all the potential outcomes of an earthquake event. All right, now I think at this point, we probably have all the numbers we need, but let's write out the long form of this so that we can first symbolically see it, and then we'll put the numbers in. So this is going to be equal to the probability of F given H and L times the probability of H and L plus the probability of F given H complement L times the probability of H complement L, and then we'll keep going. Now that we've written out the theorem of total probability for this problem, we have to pick apart some of these terms. So all of these and terms, we need to use the conditional probability rule to further define them because we know they're not statistically independent, as we proved before. So I'm just going to write out what these are using the conditional probability rule. This gives us the probability of H given L times the probability of L. These are numbers that we do have. This one, and I'm going to flip this. So I'm going to say this is probability of L and H. So you can do that using the multiplication rule. Then that's going to give us this. Probability of L naught given H times the probability of H. Then we have conditional rule here, probability of complement H given L times the probability of L. And then finally, probability of complement H given complement L times probability of complement L. All right, now we're in a situation where we can put numbers to everything. So what I'm going to do then is just plug in numbers for each of these terms. And we'll just ignore that part. Okay, so we're going to have four sets of numbers that we're putting in here. In the problem earlier, it was stated that if we have high magnitude and long duration, then the tower is definitely going to fail. Certainly, it said. So that's 1 times H given L. That was something that we were given. So that's a 0.7, and times probability of L, something that we were given 0.3. Plus the next set of terms here. This was given as well. So this was 0.05. I had to find that earlier in the problem. And then I switched this around so that we could write it this way. So the probability of not H, the probability of not L given H was the complement, and that is equal to 1 minus 0.8 or 0.2. And then probability of H, we solved for that. That was 0.26. All right. Next term, got not H given L, and that was something that was stated up front, times the probability of L, which was 0.3. And then we've got this term right here. That is also 0.3. So that's the complement here of, so that ends up being 0.3. And then finally, we come over here and we've got this term. So the probability of failure given low intensity and short duration, that was said to be 0 in the problem. So that's 0 times stuff. At this point, we don't care about that stuff because it's all 0. So now we can do the math and add all those up, and we get about 0.22 as our probability of failure given an earthquake happens. So an earthquake happens, we have about a 20% chance of failing once we add all of these different probabilities up and extrapolate them out. So this is an example of the theorem of total probability, and it also uses multiplication rule. It uses the OR rule, right, the addition rules, and then it also uses our understanding of statistical independence and mutual exclusion. So kind of brings everything together in one big package. Again, example 22-28, if you want to take another look at it.